Okay, this is the first quiz that you did on February 15th. And we've marked it, each question 1, 2, 3, and 4, and then put the marks in Moodle. Now when you go to look up your marks in Moodle, this is how they'll translate. Each of these elements in red is one of the outcomes that we reviewed at the beginning of the course. So on Moodle, when you go look up your marks for quiz 1, the first outcome is explain the action of different forces in a fluid. And that's the first part of question 1. Compare the importance of different forces, the second part of question 1. Apply dimensionless groups and apply dimensionless groups 2 for the range and the force in the dimensionless groups question on the drag. Explain the physical meaning of terms in differential equations. That's both sets of marks for number 3. Physical meaning and differential equations 2. Number 4, first part, calculate pressure in static fluids, one of our outcomes. And finally, the last part of question 4, calculate forces on submerged bodies. That's the last part of question 4. So that's how to interpret the marks when you go and look at the list on Moodle, and there'll be a mark of A, B, C, D, or F for each of these. And you interpret those as all of these are passing marks. This is an unsatisfactory result. Here's what the outcomes will look like when you see them on Moodle. This was the first question. It asked you to use arrows to show all of the forces acting on the control volume in the x direction and where they act. Identify the type of force. And I gave you this VPIGS as a hint. Viscous forces, pressure forces, inertial, gravity, and surface tension forces. Well, if we want to, we can probably neglect gravity, certainly in the x direction if x is horizontal. Surface tension forces, this is inside some kind of a channel. Here are the channel walls. Surface tension is not going to be an issue. Inertial forces are about the acceleration or what it would take to stop the fluid for two things. One, in this little region of interest right here, the fluid velocity is pretty close to 0. And for another, the fluid inertial force we only really need to consider if we're trying to measure the force the fluid exerts on something else. So, no penalty for people who put in inertial forces, but the big things going on here are viscous forces and pressure forces. P di x is c, a positive constant. P is bigger at larger values of x and smaller at smaller values of x. So P is increasing as we go in this direction. The result is that the net pressure force pushes from high pressure towards low pressure. And on this little box, there's a large pressure force pressing on this side and a smaller pressure force pressing on that side. In addition, there's viscous forces. The fluid on top is moving in the positive direction. The fluid on the bottom is moving in the negative direction. There's a velocity gradient, and if we look here, there's that velocity gradient. That's the magnitude of that velocity gradient, and that indicates a shear stress in this direction. So that was a viscous stress, and this is pressure. Likewise, on the other side, there's also a viscous stress. The velocity gradient when we get out to here is about like that. That's not quite as steep as this one, so the viscous stress acts in this direction, and it's a little smaller. Now, so we expect this one to be a little bigger and that one to be a little smaller because of the difference in the velocity gradient at the boundary of the element is where it's really important. The pressure here is larger, so the pressure force on this side is larger than the pressure force on that side. And we're told that overall the acceleration of the fluid is negative. That means that the forces in the negative x direction must be bigger than the forces in the positive x direction. So on balance, this pressure force is bigger the difference between these two pressure forces is bigger than the difference between these two viscous forces. So there's a net force pushing this way. But to get the marks for the question, you had to come up with the viscous forces, the pressure forces, show them acting in the right directions, and with the right relative magnitudes. So one of the things that I saw a lot of in this question was people adding gravity. Now that was not a force acting in the x direction, but for marking, I just ignored that. Another thing I saw a lot of was variations in the magnitude of the pressure force across the face. Particularly, I saw a lot of situations where there was a pressure force acting inwards on the top up here and acting inwards on the bottom down here. I think probably mirroring something to do with this velocity profile, but I'm not sure. Now, the pressure force is going to be positive, acting inwards everywhere in here. The pressure never goes negative. It never pulls outwards. However, if we imagine that this was the vertical direction, so that was increasing height, then in addition to the fact that there's a higher pressure here and a lower pressure there, so that P di x is a positive constant, that is, the difference between this pressure and that pressure is constant all over the cube, there might be a distributed pressure with a lower pressure up at the top and a higher pressure down at the bottom. The pressure would be lower down at the bottom only if the height, the vertical direction, was this way. So another valid setup for this one would be to say, okay, the pressure here in the middle is this much compared to that much, and that's that difference, the P di x difference from that constant. Pressure here is lower. Pressure here is higher. And there's a linear distribution of pressure on this side. And likewise, there's a linear distribution of pressure, and the pressure differences are the same on this side. So if you wanted to account for the difference in pressure with elevation, you'd have to wind up with a diagram of distributed pressure forces that looked something like that. Pressure forces acting over the entire area and increasing as you went down in the vertical direction, and with the right relative magnitudes. Question 2. A model submersible was tested in water at 20 degrees Celsius at speeds from 15 to 17 meters per second, with results for drag force as shown on the graph. So these values for force as a function of velocity plotted on the graph. Projected frontal area of the model was 0.01 square meters. If the prototype's to be the same shape, that's the same in all directions, but twice as long, so it's 2 times as long, 2 times as wide, has 4 times the area. What is the velocity range for similar flow behavior in the prototype? For part A, Reynolds number for the model must be equal to Reynolds number for the prototype. So velocity for the model times size, some length scale of the model, divided by kinematic viscosity for the model must be equal to velocity for the prototype, length for the prototype, divided by kinematic viscosity for the prototype. The model submersible was tested in water, and the prototype is to be also operated in water, so the properties are the same, and that cancels out. The velocity for the prototype, so this leads us to a velocity for the prototype equal to the length of the model divided by the length of the prototype times the velocity for the model. Length of the model is 1/2 the size of the prototype, so that's say 1 and 2 times V model. The prototype velocity range will be ranging from, instead of 15 to 17, it'll range from 7.5 to 8.5 for corresponding operating conditions. Estimate the drag force on the prototype at a speed of 8 meters per second. So that's right in the middle of this range. And that's operating at this condition, corresponding to the 16 meter per second range. So reading the drag force off of there, I make that about 258. So if the Reynolds numbers are the same, then the drag coefficients will also be the same for the model and for the prototype. Drag coefficient will be the force of drag on the model divided by 1/2 rho for the model, V for the model squared, times A for the model, equal to force of drag on the prototype divided by 1/2 rho for the prototype, V for the prototype squared, A for the prototype. So we wind up with force of drag on the prototype equal to, well, the halves will cancel out, the model densities and the prototype density will cancel out, and we wind up with V prototype squared over V model squared, and whoops, that should be area of the prototype on this side, and area of the prototype over area of the model times FD for the model. The velocity of the prototype is 1/2 the size of the velocity of the model, so that's 1/2 squared. The area of the prototype is, the prototype's twice as big, so the area will be 2 times 2 is 4 times as big. So the area of the prototype is 4 to 1 times the force of drag on the model. 1/2 squared is 1/4 times 4, cancels out, same as the force of drag on the model, equal to 258 newtons.